So this lesson starts on page 4 of your unit handout. It's called Rationalizing. It's Review Part 2. I had mentioned that when you're doing a lot of the algebraic work in this course that takes you to the answer to a problem, there's two main tools that you have to employ: factoring and rationalizing. And it isn't going to be that you blindly start factoring everything or just automatically rationalize. It's like literally having two tools in a toolbox, a screwdriver and a hammer. If I put a board in front of you with a nail in it, you're not going to try to use the screwdriver. I hope not. You're going to say, oh, the hammer is more applicable. Sometimes in getting to our goal, factoring is what you need to do. Sometimes rationalizing is what you need to do. Sometimes you need to try both of them. So I'm going to remind you that in grade 11, I think, in Math 20-1 is the first time you were told, we don't like denominators that have radicals in them. And the reason probably isn't taught to you. There are a number of reasons, but really they're artificial. One of the reasons is it's easier to add fractions when the fractions have denominators that are whole numbers, and that's certainly true. One of the reasons is apparently that things are simpler if they're rationalized in terms of the denominator. And I've never liked that, because if I have something like 4 over root 273, and you rationalize that, what you're going to end up with, and we won't worry about y just yet, what you're going to end up with is this. And I believe I would make a very strong argument for the fact that I don't believe that second expression is, quote, simpler than the first one. I don't. To me, the first one looks simpler. So I think anybody who says, well, that's why, sometimes it makes it simpler, but sometimes it doesn't. So now we get to calculus. And by the way, all I'm doing here is I'm multiplying the numerator and denominator of this 4 over root 273 by root 273 over root 273, which is 1. I'm not changing the value. Okay, and that's how you rationalize the denominator if the denominator is a monomial. Now, we get to calculus, and I will tell you this. It isn't that you rationalize the denominator, or it isn't that you rationalize the numerator. You rationalize whatever will make the expression simpler in the end. And the curious thing here is it's not always going to be obvious. So sometimes you might have to rationalize the denominator and see if it simplifies the expression. Sometimes you might have to try rationalizing the numerator. Now, in our examples that I'm going to go through today, and I will just show them to you briefly, if I gave you this expression, root x plus 3 over x minus 9, and I said simplify it, you open up that toolbox, and you see a factoring tool, and you see a rationalizing tool. Well, there's nothing to factor there. So you're going to rationalize. Well, what are you going to rationalize? The numerator, because it's got a radical in it. And this is almost like doing trigonometric proofs and identity work in Math 30. You have to try something and see if it bears fruit. You have to try something and see if it's going to give you a pleasant result. And just like the analogy I use in trigonometric identities and proofs, if you start walking down that road, trying these things and taking step after step, and the road gets narrower and darker and you hear growling coming from the bush, go back and try something different. And what I'm getting at here is you have to have that mindset that you're going to work on something like this, and this is a simple one, by the way. You're going to work on something like this, and if your work leads you to a mess, go back to the beginning and try something different. It's not always going to be a linear path that we have to follow. So now let's talk specifically about rationalizing. In this course, you're rationalizing either a numerator or a denominator depending on your needs, okay? And you will get more experience with that. If you have a radical that's a binomial, like root a minus root b, root a minus root b can be rationalized. Maybe I should say, rationalized means have no radicals. no square roots. Root a minus root b can be rationalized if you multiply it by its conjugate. So root a minus root b and root a plus root b are conjugates. Okay. Why does this result in rationalizing the expression? Well, if you multiply two conjugates together, you end up with a difference of squares. Now, I could certainly do the following. I could say FOIL, and first would be root a times root a, which is a. Outer would be negative root b. Outer would be root a times root b, which is root ab. Inner would be the product of these two, which is negative root ab. And last would be negative root b times root b, which is negative b squared. And of course, with conjugates being multiplied, the outer and the inner will automatically be opposites of each other. So you're left with a. Did I say b squared or did I just write b squared? I said b squared. I should have said b. Root b times root b is b. So you're left with a minus b. You're left with a difference of the squares of the root a and the root b. Again, if you're multiplying conjugates, I believe I mentioned this yesterday, you don't have to FOIL, you just go FLA. You just go first and last. But the bottom line is you end up with a minus b, and there's no radicals. That's the important aspect here. It's a difference of squares, but we're not factoring it, we're bringing it back in by multiplying. So, example 4, rationalize the numerator of this expression. Let's rewrite it so you have some room to work here. You have root x plus 3. I will often put that little on my square root sign, in case you haven't seen this before. I will often put this little thing to indicate that that's where the square root is ending. Sometimes it's not clear, but it's definitely ending at the x. And this is over x minus 9. Now, you open up that toolbox, you're asked to simplify this in some way. Pretend it doesn't say rationalize the numerator. Is there anything that's factorable? No. Everybody shakes their head no. Okay, we'll come back to that in a bit. So you say, I'm going to rationalize the part of the radical, or the part of the expression rather, that contains a radical, and in this case, I'm going to multiply by root x minus root 3, or minus 3, root x minus 3, because that's the conjugate of root x plus 3. You're going to get a lot more experience with all these little details that I'm throwing in and I'm sprinkling on the lesson. But one of the things you need to understand is that you're not going to multiply out the part that you're not rationalizing. The x minus 9 times root x minus 3 is going to be left as those two factors. So we have in the denominator x minus 9 as a factor and root x minus 3 as a factor. When you multiply out the numerator, we square the first and subtract the square of the second, and you get x minus 9. Is it clear why we didn't want to multiply out the bottom now? I hope it is, because now what we have is this factor of x minus 9 in the numerator and denominator. And remember, I've tried to drill this into your heads for a couple of years for some of you. A factor is something that is in its own set of brackets being multiplied by the other stuff. And you're only ever allowed to cancel factors. So x minus 9 and x minus 9 are gone. And we're left with 1 over root x minus 3. And that's the answer. So the original expression is in the top of the screen in brown. We rationalized the numerator by multiplying the numerator and denominator by the conjugate. Multiplying out the top gives x minus 9, which cancels with the x minus 9 in the denominator. Any questions in getting to the final answer of 1 over root x minus 3? Okay, I have a question for you now. So this is the answer. In this course, we need to be able to think outside of the box at times. It makes our lives a lot easier. And if I said to you, let's talk about x minus 9. Is there a greatest common factor other than 1? Well, no. Is it a quadratic? No. Quadratic trinomial? No. Can we factor by grouping? Well, that's kind of just one step away from insanity because you need 4 terms. Is it a difference of squares? No. Yeah, it is actually. If I said to you, is it a difference of squares? Most people would say no. So if I said to you, on the other hand, and this is how I've taught differences of squares to you, is x squared minus 25 a difference of squares? The answer is yes, correct? I would say to you, is x squared a perfect square? And everybody would say yes. And I would ask Liam, what is x squared the perfect square of? And Liam would say x. And then I would say, is 25 a perfect square? And everybody would say yes. And I'd ask Evan, what is 25 the perfect square of? 5. And that's why this factors into x plus 5, x minus 5, and everybody's happy, and you don't have any problems with it. It's easy, right? So let me run through those questions over here. Is x squared is x minus 9 a difference of squares? Okay, first of all, is x minus 9 a difference? Yeah, there's a minus in there. Is 9 a perfect square? What is 9 the perfect square of? 3. That's child's play. So if we can factor this as a difference of squares, and how many of you see exactly where I'm going with this? If this is factorable by a difference of squares, we can put plus 3 and minus 3 there. Don't forget we have root x plus 3 in the numerator. And then I say to you, this is calculus. This is in grade 9 or 10 or even 11 math or even math 30-1. Is x a perfect square? The answer is anything, as long as it's not negative, is a perfect square of the square root of the thing. X is the perfect square of the square root of x. So x minus 9 factors into root x plus 3, root x minus 3. Now, how quick is that to get to the answer compared to rationalize? I'm not saying this is always the route you want to go. But you are no longer limited to perfect squares being things like 25 or r squared or r to the 8. I hope it's clear we're left with the same answer, 1 over root x minus 3. And I guess what I'm saying is, if the need suits you, you could factor this as a difference of squares, or you could factor it as a difference of cubes if you really wanted to. The thing that you square to get p cubed is p to the 3/2. Because when you multiply 3/2 by 2, which is a power of a power rule, you get 3. That means this factors into p to the 3/2, that's a 3, minus 4, p to the 3/2, plus 4. I think many of you will see, well, maybe I will ask this, how many of you see there's kind of no end to what you could do here? But that doesn't mean you do it. You do it if it's going to help you out. I mean, I could factor this as a sum of cubes if I wanted to, by saying p to the 3/2 is p to the half cubed, and 4 is the cube root of 4 cubed. But then it's almost like an infinite regress that you just keep going further and further. I would only ever do that if it's going to be helpful to me. And I'm not doing this to put this heavy burden on you that, oh man, now I got to remember that. I'm doing it so that when you're working on stuff, you might recall, hey, maybe I can try this. Again, this is not about linear thinking. It's about taking all of your skills and using them when you need to. So does anybody have any questions about this method in going from here to the answer? And by the way, when I said, is x minus 9 factorable in Farhan, you kind of said, yes, that's what you had in mind? Yeah. Okay, we have one more example I'd like to look at with you today. So rationalize the denominator. Well, if you're going to rationalize this, clearly you're going to rationalize the denominator because it's the only thing that has radicals in it. I highly recommend rewriting this so that you have room to show all of your work. When you take a look at how big this stuff prints out on paper, I don't think anybody really writes that small. Some of you might. Apparently some of you do. Okay. So I'm going to multiply the numerator and denominator of this beast by the conjugate of the thing I'm trying to rationalize. The thing I'm trying to rationalize is root x plus 2 minus root x minus 1. So I have to multiply by root x plus 2 plus root x minus 1. I'm sure some of you remember me telling you this I just want to check my work, telling you this in Math 30-1, and if you didn't have me for 30-1, you might remember it from 20-1. And if you haven't had me before, I'm going to say it a lot here. At this level, when you're doing algebra that involves many steps, you should really get in the habit of doing each step twice. If you're like me, and maybe you're not, hopefully you're not, I just go on autopilot sometimes and I just start writing and it just comes out of my brain. But with that comes errors. So you just want to make sure that you copy things down correctly, check from step to step, and I think this looks fine. We are going to leave the numerator in factored form. And we are going to multiply out those two conjugates. Of course, when I multiply out those two conjugates, everybody, I don't need to FOIL. I can just take the first times the first minus the last times the last. That's the point of having conjugates that are being multiplied. Are you with me on this? Okay. So when I multiply the root x plus 2 times the root x plus 2, I am left with x plus 2. And then I said minus, when I multiply this by this, I'm left with x minus 1. And again, wait for it though. I was making this mistake that I've just made on the board when I was in grade 12 in high school, because no teacher had ever bothered to explain this to me or the significance of it to me. And that meant that even though I was capable of understanding the math we were learning, there was this little step from junior high that was screwing me up. I will not get the right answer here. And how many of you know what the problem is? Makai, what do I need to do? Right, I need to have brackets around the x minus 1. If I don't subtract x minus 1 in brackets, then I'm not really subtracting x minus 1. I'm subtracting x and then I'm subtracting 1. And what I need to be doing is subtracting x and subtracting negative 1. The denominator of this becomes 1, which is really fortuitous, lucky for us. X minus x is 0. 2 minus 1. Oh, no, it doesn't become 1. It becomes 3, doesn't it? 2 minus negative 1 is 3. So I'm left with x squared, and then root x plus 2 plus root x minus 1, and this is over 3. Be over 1 if I forgot the brackets. Any questions with that example? Go ahead. Could I have done it by factoring it instead? I would say no. And this, I'm glad you asked, because if I thought of the denominator as a difference of squares, then the thing that I square, this is going to be difficult to follow, the thing that I square to get the square root of x plus 2 is the fourth root of x plus 2. And what that would mean is that this piece, if I did factor it as a difference of squares, would become that, which we're digging a hole here that we don't want to dig, figuratively speaking. We're climbing into something that if we go much further with this, you might have a hard time climbing out of that hole. So this is what I meant with my analogy that, you view this math as kind of, you're being lost on a dark road. You have to find your way home. You don't just shut down and stand there. You start walking. But this path takes us to a more bumpy place, a scarier place. So we go back to the beginning and we try something different. Any other questions with that example? Should we multiply this x squared through? The answer is no. And here's my response to why. There's nothing in it for us. It's not going to get us anything. In fact, when I said earlier, and I don't know if it was Farhan or Arden that had asked about the negative exponent, can we just leave it as x to the negative 1? I said we want positive exponents. I'll go one further and say our expressions need to have factors raised to positive exponents. We don't want things multiplied out. We want to see factors multiplied by factors. And I don't want to get into why in a lot of detail other than to say one of the things you're going to need to be able to find out eventually is what values of x make the numerator of this expression 0 and what value make the denominator 0. The only way to do that is to set each factor equal to 0. And as soon as you multiply the factors through, it's like a polynomial. You multiply it through, you lose sight of the zeros. You don't know what the zeros are anymore. And if you did not complete Math 30-1 yet, you don't understand what I mean by polynomials, but that's okay. So no other questions? So on page 4, questions 1 and 2, I don't want you necessarily to jump to the challenge problems right away, but I would like you to try these two challenge problems. Because it's my way now of explaining to you why we're doing what we're doing. Okay? We're doing what we're doing because sometimes you'll have an expression like this. And you really want to put the number 8 in for x, but you can't. Because it's non-permissible. The cube root of 8 is 2. 2 minus 2 is 0, so you would get division by 0 happening. But we still want to put 8 in. So these two tools, factoring and rationalizing, are ways for you to change the appearance of the expression so that you can put that number in. So these are good exercises in preparation for what's around the corner. And I want to say just a couple more things, and then I'll be done. First of all, if you are in Math 30-1 right now, everything I say from here on in is going to be lost on you. But I want to try to make a connection between what I'm talking about here and rational expressions with wholes. If you have a rational expression with a whole, can anybody tell me, does anybody remember how you know there's a whole by looking at the rational expression? Farhan? Can you repeat that, please?
There's a factor in the denominator that isn't canceled with a factor in the numerator.
Other way around. There's a factor in the denominator that does cancel with a factor in the numerator. Now think about this for a second. If there's a factor in the denominator that creates a 0, because you put x equals 8 in and you get 0, that means there's x minus 8 as a factor in the denominator. But if there's also a factor in the numerator that's identical, that means when you put x equals 8 in, you should get 0 in the numerator as well. In other words, I want you to notice, all of you, not just the people who have completed 30-1, that when you put 8 in here, not only do you get divided by 0, you get 0 over 0. And when you get 0 over 0, with one exception, when you get 0 over 0, it's always going to be possible, with one exception, to do something to it so you can put the number in. And some of you might recognize that what we're kind of talking about here is finding the y coordinate of the whole. Okay? So if you take a look at number 2, if I want to put 2 in for x, and you put 2 here and here, you would have root 6 minus 2 minus 2 over root 3 minus 2 minus 1. What do we get in the top? You get root 4 minus 2, which is 2 minus 2, which is 0. And in the denominator, you get root 3 minus 2, which is root 1. Root 1 minus 1 is 0. I'm telling you that it's possible to use your mathematical magic to do something to this expression so that you can put 2 in and calculate the value. Okay, and I'm having this 5-minute discussion with you now so that I don't have to have a 30-minute discussion with you later about this. We can talk about it for another 5 minutes when the time comes. And the answers are here. Everything that I've said about these challenge problems is not part of today's lesson, but if you understand it and you can do the challenge problems, you will be better off later on. That's not going to be up visible to you for much longer, so either take a screen capture of it or take your phone out and take a picture of it, because I'm going to be switching screens right away. So get to work. When you have a question, let me know. Everybody that is here remotely, Demi, Zach, Nicole, and Ben, just type something in chat. I'll keep my eyes peeled, and if I don't respond right away, just turn off your mic and say something, and I will respond. And a quick poll for all of you remotely, because I always like to check on every student. Just let me know, did that go okay today in the chat? Just let me know.